Good afternoon. I think we should just get this started. I would like to welcome you all to this webinar on sustainable materials hosted by IOP Publishing, particular Journal of Physics Materials, which is part of the Journal of Physics series of journals within the IOP. My name is Magda Titirich. I'm a professor of sustainable energy materials at Imperial College London, and it is my pleasure to host this webinar, which follows up a roadmap on sustainable materials, which we have published recently. Today, unfortunately, we can't accommodate everyone that contributed to the issue, but we'll have some great presenters across important areas in sustainability. So there is Aggie Brand-Tabot, and she would tell us how you could actually source sustainable raw precursors from biomass. We have Silvia Vignolini, and she will tell us about how you could engineering and self-assemble cellulose nanocrystal so we could make structural colors, which is a very sustainable way of producing color rather to the very unsustainable dyes and so on. We have Kunyang Lee, who will tell us how you could use plant-based materials to actually create building blocks to make strong nanocomposites. Heather Au will tell us about basically how you could take biomass precursors and carbonize them so that you can create sustainable platforms for batteries or energy storage technologies in general. And finally, we have Goran Finven, who will tell us about how we could actually assess the sustainability and decide if a product or an application is actually sustainable. So as I said, this is part of the sustainable roadmap, which I have led myself, and is being created with the hope to add the development of why the sustainable materials research community provide a guide for academia, industry, government, and funding agency. It's quite a large roadmap, and it has 28 sections, and it has about 55 authors. And I think I've already presented you the speakers at the start. I can show you their picture. This is Aggie, and this is Sylvia, and this is Kunyang, and Heather, and Goran, and you'll have a pleasure to listen to each of them very soon. So I guess with no further ado, we'll start this with Aggie Brand-Tabot, who is now a lecturer in the Department of Chemistry at Imperial College London, and she will tell us about how you could isolate sustainable material precursors from biomass. And I guess I need to stop sharing.
It looks. Sorry, folks. Hi, Magda. It's Alex here. Hello. It looks like Aggie's gone offline, folks. I'm terribly sorry. So, Lily, do you think you could pass control to Sylvia? And Sylvia, are you?
Yes, it's
fine.
You
ready to go? That would be wonderful. I'm terribly sorry. We just lost Aggie offline there for a moment. So, if you're able to jump in, Sylvia.
Okay, then change in plane, and we'll start with Professor Silvia Vignolini from the University of Cambridge on biomimetic color engineers from nature to applications.
Can you see my slide?
Yes, it looks great.
Okay, so I'm going to talk a bit about color, because we often don't think about color in terms of sustainable materials. but actually color are everywhere surrounding us. And if you're looking at this simple picture of a supermarket, you can see already that the packaging, for example, of all these products is colored. And the problem is, how do we make color? Yes, and how can we make sure to make color in a more sustainable way? Because today there are several problems that goes with the traditional production of coloration. So you have on one side the traditional color that are obtained by pigment that consumed a lot of water, and unfortunately chemicals that then are disposed in the environment. And effect pigments that are this color that are a little bit more metallic, that you often see in glitter, in fact, also, and the pigment that you see in the car, that are made with inorganic material that have been proved to be not only negative and having a negative impact on the environment. For example, for the microplastic and plastic glitter, a lot of this material is actually then directly disposed into our sea, contributing to the microplastic problem, but also to our health. In fact, lots of these inorganic nanoparticles that are exploited for this pigmentation, that are also found not only in the packaging in the car, but also in the food that we eat, are often made out of nanotitania that has been recently banned actually this year from the European community. So there are several problems around this type of material, and therefore it's important to find a solution that is not only beneficial to us as humans, but also in general that is not that doesn't have a strong impact in the environment. And interestingly, plants use a material that is surrounding us everywhere, that is cellulose, to produce this coloration. In fact, there are many different types of plants, and these are just few examples, that instead producing color and this blue coloration with a blue pigment, a blue dye, they exploit cellulose, and cellulose is just a polymer that is in the plant cell wall. And the reason why you can create color with this cellulose is it's because the cellulose in this species of plants is organized into a helicoidal architecture, and the helicoidal architecture is reported here in the slides. I hope you can see it. And essentially, when you observe this arc pattern made out of the cellulose nanofibers, and when this arc pattern is comparable with the wavelength of the light, you can achieve a strong reflection of a coloration. So by simply changing the distance between these fibers inside the cell wall, the plants can really produce a wide variety of color. And interestingly, we can do it as well in the lab. So we can borrow not only the architecture, but also the building block, the material, the cellulose. And this is interesting because cellulose is the most abundant biopolymer that we have available on the planet. It's edible and biocompatible. In fact, when you say that you have a diet that is rich of fibers, it's actually these fibers are cellulose fibers. And cellulose is one of the most exploited material in our society because it's so abundant. And you just need to think about paper, but also all the pharmaceutical market or all the glasses that you are wearing are made out of cellulose derivatives. Yeah, so it's a really common polymer. What we use so-called cellulose nanocrystal, that are the small nanoparticles that are isolated directly from cellulose, from biomaterial, biostock. So essentially like wood pulp or even standard cotton, and can be isolated also from used textiles. And the cellulose nanocrystal have a special properties. They can self-assemble, meaning that if you put them in a water suspension, they spontaneously try to form an helicoidal architecture that is really similar to what I've shown you before in the plants, and therefore you can create color. And my group, just to give you a flavor of what we do, has been for many years working on the fabrication of this color, and we recently have worked on making them on a really large scale. And these are just examples of laminates of cellulose that are long several meters, where we can obtain a color simply using this cellulosic material. And once you have these big laminates, you can essentially make pigments, pigmented particle, or also glitter that can be then redispersed and obtained as a proper optical photonic pigments. So with this, I hope that I convince you that cellulose as well can be used as a pigment, not only as paper. And I would like to thank you for your attention.
Great. Thank you very much, Sylvia, for this very enlightening talk. It's wonderful what you could do with cellulose if you assemble it properly. We'll have questions at the very end for all the speakers. So I think we have Agi back online. And so maybe we'll just move back to Agi and again to how do you actually extract such cellulose and other raw precursors from biomass sustainably. As I said, Agi is a lecturer in the Department of Chemistry at Imperial College London. Please, Agi.
Okay. Hi, everyone. Apologies. I'm glad that it was just a brief outage. Thanks, Magda. I'm Agnieszka Agi-Brandt-Taubert, and I want to give you a quick overview of the section that I wrote for the roadmap article, which is isolation of sustainable material precursors from biomass. Okay, so there's a lot of biomass around the world, and I think there's enough to make all our sort of carbon-based materials from biomass in principle. It's worth noting that especially the more sustainable precursors don't occur in a pure form, and they generally need to be separated from their, or purified from the matrix. I call the purification a central operation in biorefining because it has a lot of impacts because it's quite early on in the materials production. I've put first the economic aspects because really the cost is important, especially if we're looking to replace petrochemical materials, which tend to be cheap because we have a very scaled petrochemical production today. Aspects that affect the cost of the precursor that we're purifying are the energy input, the chemical input, how complex the process is, and also how successful our purification or the isolation is. So the purer and the more defined, typically a fraction, the higher the value will be. It will also affect the sustainability. If we need a lot of energy, then the then the sustainability will be lower. If we're using chemicals that are harmful either to the workers or maybe to the once they get to the environment, that is also reduces the sustainability. And there might also be side products that we are forming from as we're purifying our target precursor that might enhance or reduce the sustainability. And the operation, because it usually involves chemical steps also, or mechanical steps, has an impact on what application we can actually use the precursor. This is the figure that I've put into the section, and as you can see, there are two, I've grouped, there's lots of different isolation methods, and I've grouped them into two classes. So one group is the extraction and fractionation, which tends to occur at lower temperatures, and then there's the thermal conversions, which tend to happen at higher temperatures. And we're getting a whole range of sort of like bulk precursors that we can then make materials from, and they are proteins, sugars, lipids, lignin, cellulose fibers, which Sylvia just talked about. And when we do thermal conversion, because there a lot of the bonds in the biomass break, we get fractions that are mixed, and they're called gas, bio oil, or biocrude, and char. And what's again saying is sort of a central step and embedded. So we will be making the bio-based materials alongside food production, alongside our energy is very important. Our energy production and yes, the materials production will be embedded in other processes. Just to give you a flavor of the chemistry that we're looking at, so here I sort of grouped them again. A very important one, as Sylvia just mentioned, is cellulose, which occurs in our paper and cotton products today. They're all sugars. There's the chitin, which is a biopolymer in crustaceans. like shrimp shells, and starch we use already for food. So it's, for example, in maize, but you can actually, the biggest bioplastics range at the moment is starch-based. There are polyphenolics, there are lignin, there's a native lignin, but usually the lignins that we get out of a sort of fractionation step of a lignin containing biomass are different. They're industrially isolated, like lignosulfonates or Kraft lignin. And then we are also already using proteins. There's, for example, animal hair or silk, but there's also a lot of plant proteins that we're not using at the moment. And we can isolate those. There might be some really interesting material applications coming up in the future. As one example, how sort of biopolymers or precursors are isolated. So this is the work that I do a lot, is fractionating the biopolymers in lignocellulosic biomass. So there's cellulose, there's lignin and hemicellulose, and there's sort of two different approaches. One is very low cost, but the separation is not very clean. And then there's chemical-based one, which includes the current industrial pulping methods, and some new ones where we're using chemicals to remove the lignin at an earlier stage, so we get a more pure cellulose, but there the chemicals very soon, unless you're using a dilute form of a very low cost acid, we have to recover those chemicals very well, and that's a big challenge, and it adds to the process complexity and cost. Just to give you an idea of what sort of products you might be getting if you're going down the thermochemical conversion of, again, lignocellulosic or wood biomass. So here I've picked out the pyrolysis oil and just a flavor of what sort of chemicals you can get, and see they're small and there's quite a few. So it's a simplified composition of the pyrolysis oil, and you can see the challenge of separating comes after the sort of like heating stage. Yeah, in summary, there are very interesting precursors that can replace petrochemical materials. There's two different approaches. One where you sort of like, it's a gentler approach, but you need to be kind of very savvy with your chemicals that you're using, or the thermochemical conversion where you're heating it in the absence of oxygen. And while some industrial processes exist, like wood pulping, we need to invent many more if we want to make a broader range of products, and we really need to collaborate with everyone in the value chain to piece the right technologies together. Yeah, thank you for listening.
Thank you, Aggie, for this talk. Can you hear me? Hopefully.
Yes.
We move to then the next speaker. So back to cellulose, and I have the pleasure to introduce Kunyang Lee. He is in the aerospace department at Imperial College London. He will talk about nanocellulose again as a building block for sustainable nanocomposites. Kunyang, over to you.
Thank you, Magda. Right, hopefully everyone can see my screen. So my name is Kunyang. I'll talk about using nanocellulose to make sustainable composites, especially addressing what it is, the challenges, how do we get around them, and what could we expect in the next sort of 10 to 20 years. So the general idea of using nanocellulose is the fact that we need more renewable materials that are recyclable or derived from renewable resources. Now, there are two ways of achieving this. You either get a very good chemist, train the chemist in the lab, force the chemist to make plastics out of plant oil, and that could take years or decades to achieve. Or you take existing materials, existing polylactic acid, for example, existing cellulose, for example, combine them in a creative way to at least fill in this time gap between truly plant-based, fully renewable resources and this the fossil-based economy. And this is where cellulose comes into play. So how do we achieve this? Effectively, we are going to use a composite approach, right? That you actually combine cellulose with, as the reinforcement, with a suitable polymer matrix. Ideally, the polymer matrix should be sustainable. The matrix protects the cellulose fibers. The fibers carries the stiffness, the strength. The interface between the fiber and the polymer matrix is an important design parameter that allows efficient stress transfer to achieve maximum performance. Now, why do we care about cellulose in this context, right? So if we consider wood as an example, typical wood has modulus of 5 to 15 gigapascal, strength 120 gigapascal. As a standalone material, it is a good enough construction material. If you pulp it down to the extreme right, effectively a cellulose molecule, in those cases, you're trying to break that carbon-carbon bond, probably about 20 gigapascal to actually break that carbon-carbon bond. But what we're interested in is that particular length scale, that sort of cellulose microfibril, elementary fibrils, bundles of fibrils type length scale with sort of dimensions of approximately 50, 60 down to sort of 4 nanometer in width. At those length scale, your modulus is up to 165 gigapascal. That is twice as much as glass fibers. At that length scale, those nanofibers, they are 6 gigapascal. So that's actually twice as strong as glass fiber. So that actually provides us with an interesting alternative to actually replace glass fibers with these sort of cellulose nanomaterials. So there are two types of cellulose nanomaterials. You can take wood pulp, you pulp it. After you delignify that pulp, you pass it through high pressure homogenizers, grinders, microfluidizers to produce this wood-derived nanocellulose. Typically in the literature, you call these things cellulose microfibrils or nanofibrils. You see the SEM images on the bottom right corner. Or you can actually grow this cellulose yourself through bacteria. You feed bacteria nutrients, bacteria is happy, start to produce something for us, and that something is that little gel on the top right hand side corner. It is actually a fibrous net of sort of 50 nanometer fiber width, and it is chemically pure without hemicellulose. These things are very crystalline, 90% crystallinity, and in the literature you see them known as bacterial cellulose or BC in general. So the greatest challenge with nanocellulose processing is the irreversible hydrogen bond formation. When you have wet state, when you dry it, it turns into a piece of paper, you put them in the water, it doesn't go back to the rehydrated state. Second problem is that it is very expensive. We don't know the exact price at the moment, but loosely speaking, $8 per kilogram wet is about the ballpark figure. So that's 1% solid content. If you basically take the number divided by 0.01, that gives you the dry state value. And that is too expensive for any useful materials, right? So this is where our group comes into play. We basically champion the idea of simple design. We do not want to do crazy chemistry. From the very early on, we look at manufacturability, so simple lamination like Silva was talking about earlier in the first talk, and we are looking at exploiting all the radical effects that cannot be achieved by conventional materials. So in this case, two-dimensional cellulose nanopaper. You press them into a piece of paper, infiltrate with a polymer, cure it. So polyazole is a very soft plant-based polymer that has no modulus and no strength. Adding this cellulose nanopaper into it, you can easily push the performance up to approximately sort of 3-5 gigapascal or so at a strength of 20 megapascal. Huge performance boost with introducing nanocellulose into the system. We can also throw this nanocellulose nanopaper into a transparent resin. You can make everything ultimately transparent and use this thing as reinforcement for bulletproof glass. In fact, adding just small amount of cellulose, you can actually push everything up by 60% in terms of impact strength compared to a gold standard impact modified acrylic. Now, that's not so much on sustainable materials per se, but making transparent armor lighter reduces fuel consumption. And from that aspect, it is actually more sustainable from a transportation point of view. Now, we can also look at using nanocellulose and that hydrogen bonding formation to bind loose fibers together. So the design is that you disperse nanocellulose with bigger fibers, remove the water, press them, the nanocellulose binds together, forming this irreversible hydrogen bonds, ultimately producing a fiberboard. Now, these fiberboards do not need any glue. You have nanocellulose, you have, in this case, sisal fibers or any other fibers you can think of, put them together, press them out, you get a very rigid board. How rigid are we talking about? So the top two pictures are a rather sort of fiber network, size of fiber network without cellulose. The bottom two have bacterial cellulose added to it. You can fill in a glass of water. It can sustain the weight of a cup of water, doesn't deform at all, whereas the ones without cellulose, it deforms quite easily. You can make it as big as possible because this is a simple paper making process. So that is actually a rather big piece of materials that the student there was holding at the bottom. It doesn't flex. And you can actually create art pieces out of it to replace your fiber boards that typically contains about 10% formaldehyde glue with just this nanocellulose. So to quickly sum up, right, the use of nanocellulose as reinforcement polymers was first mentioned in a paper published in 1987. Actually, around that period, that 15-year period, people are trying to figure out how to make nanocellulose. What the hell is nanocellulose? It effectively is just a scientific curiosity. And then sort of 2000 onwards, people start to realize we can do a lot of clever things with nanocellulose. They start to do a lot of proof of concept research to show that it will work in various industries. You use cellulose as reinforcement is actually one of the ideas that stem from that. Now, in 2015 onwards, we have critical mass. Multiple universities have nanocellulose research. What we are missing is a commercializable product. Effectively, what we call a nanocellulose in a particular killer application. And we believe that the way to get there is simple design, manufacturability, and radical effects as the core design principle. With that, I thank you for listening. Thank you very much.
Thank you very much, Kun Yang, for this fascinating talk on how you could use cellulose to make lightweight and mechanical strong composites. Next, we'll move to Heather Au, who is a Faraday Research Fellow in Chemical Engineering, also at Imperial, and will switch gear now from pure biomass to carbonized biomass and the use in energy storage. Heather, over to you.
Great, thank you. Just to check, you can see my screen, right?
Yes, perfect.
Okay, great. So I'll tell you a bit today about the work we do in the group on sustainable carbon materials for energy storage. So I don't need to tell you that our global energy consumption is rising, and batteries will be one of the key technologies that will enable our transition to net zero by providing reliable grid energy storage for renewable resources, by providing alternative power for transportation such as our cars, buses, and possibly even aeroplanes. So we already use batteries today in a wide range of applications, but it's one technology really that dominates the market, and that's lithium-ion batteries. So a battery consists typically of a cathode and an anode, and then during discharge, the ions move from the anode to the cathode and the electrons move around the external circuit, and then on charge, the reverse motion happens. But there are many components that make up a battery, so not just the active anode and cathode materials, but we also need metal foils on both the electrodes, and then we have the electrolyte, the separator, and then also normally a carbon black and a binder material. So if we consider just the active materials, the anode is typically based on graphite, and the cathode material contains lithium and cobalt. And these are geopolitically compromised materials. They're concentrated in the globe. And the question is, do we have enough of these materials for our projected future consumption? And the answer really is no. In terms of the other components in the battery, you also rely heavily on copper at the anode. And then we also have fluorine-containing species in the electrolyte and in the binder that will present problems further down the line. So the question is, how can we make batteries in a better way? And there's no one single solution here, really. The answer is that we need to diversify the range of battery chemistries that we use to address performance, economics, and sustainability. So here on the right, we have various different new battery chemistries that are being explored in their projected gravimetric and volumetric energy densities. And there are different ways of developing new technologies. So one way is that we replace the lithium ion for more abundant metals such as sodium or potassium, or multivalent ions like aluminium or magnesium, zinc, calcium. Or for applications where we do still require high energy densities, then we keep the lithium, but we can replace the cathode material for more abundant materials that have higher capacity, such as sulfur and oxygen. So in the work, in the group, we look at various ones of these technologies, but one of the main ones we study sodium-ion batteries, and specifically we look at hard carbons for sodium-ion battery anodes. So why sodium? So sodium and lithium have very similar chemistries, really. They share similar electronegativity values, similar standard redox potentials. But in terms of global abundance, sodium is obviously far more abundant than lithium. We can replace other components inside the battery, such as the current collector, for cheaper and more abundant alternatives. But in terms of the chemistry and the processing, because they are quite similar, it means there's no extra cost required to replace lithium technology with new sodium technology. One of the drawbacks, though, is that sodium has a higher ionic radius. So that means in terms of the projected energy density, we can't necessarily reach as high as we could for lithium-ion technology, but that means it's more suited for stationary storage applications. So we use a method in the group called hydrothermal carbonization to create hard carbons from biomass. And this is a really valuable tool because we can take something that's otherwise a waste material and turn it into something valuable. So we can start with any biomass precursor, but at its simplest, we take a sugar molecule like glucose, and we hydrothermally synthesize this at a relatively low temperature, and under self-generated pressure, we form some carbon spheres, which we can then pyrolyze to obtain a conductive carbon material, which we can then use in the battery. So it's a really nice versatile technique because we can tune the porosity and morphology very easily on these carbons by just varying the synthesis conditions and the precursor.
I'm not sure, but I can't see the slides changing anymore.
Oh, okay. What if shall I stop sharing the screen and try again?
Oh, no, yes, perfect. Yeah, that's good.
Yep, okay, all right. Okay, so just to continue then, so we can also tune the carbon surface then using this additional thermal treatment. And so we can tune the surface chemistry and electronic properties. So we derive these really nice spherical particles from our synthesis method, and we can finely tune from the microstructure all the way down to the nanostructure, just purely by controlling the pyrolysis temperature. So it's really very simple. And then tuning the structure really is the key to optimizing the sodium-ion storage. So there are various different structural features in the carbon that can store sodium, and we can exert control over the pore size, the interlayer spacing, and the level of defects on the surface. And we see when we build the sodium-ion battery that we can really change.
I still think you're not changing the slides again.
Is it not changing now? What if I click like this? Is anything appearing or disappearing?
No.
Okay, what about now? Have I changed the slide?
No, I think it's blocked. But anyway, I think just carry on, or I don't know, because we don't have much time.
Okay, what if I share the screen now? Sorry, can you see that?
That's good. Yeah,
okay.
Carry on.
All right, so we can tune the structure of the carbons very nicely, and then we see how we change the capacity of the materials. So maybe I'll skip these slides, but this is just to say that we carried out a range of different characterizations to really try to relate how the sodium is being stored inside the carbon structure. So we conducted in situ dilatometry and sodium NMR, and also coupled that with DFT studies and ex situ XPS to understand how the sodium is being stored and what decomposition is happening on the surface. And that means that afterwards we can really take that structure and then use it to feed back into the hydrothermal synthesis process to really optimize these sodium materials. So then, as I mentioned earlier, sodium, it can't necessarily reach the same capacities or energies as we want with lithium. So another technology that we also work on in the group is lithium sulfur batteries, because they have a very high projected energy density. And for that, what we really need to target are freestanding configurations. And so in the group, we target freestanding electrodes based on lignin because it's the cheap and abundant byproduct of the paper making industry. So we can use a nice sustainable non-petrochemical precursor. And we use the lignin to spin carbon fibers, which we use as electrode supports in the battery, not just on the lithium side. So we see here the lithium plated onto the surface of the fibers, which means we can really reduce the total amount of lithium necessary in the cell. but we can also use it on the cathode side to support the conversion of the various sulfur species inside the battery. And if we compare that performance then to a commercially available cathode material, we can see that we can actually reach double the specific capacity and doubling the energy density just in the electrode alone, which is a very promising performance already, and this is from a sustainable precursor. So hopefully I've shown you that it is possible to solve this energy trilemma if we diversify our battery chemistries based on abundant materials where possible. And this through if we find value from waste materials. So I've demonstrated the use of biomass-derived carbons in 2 different applications, but carbons could be applicable across all of the different battery technologies. Right, thank you for listening.
Thank you very much, Heather, for this insight into more sustainable batteries. And finally, luckily, we have Goran Findan, who will end up our section with something that is extremely, extremely important, in particular for people like me and the previous speakers that make materials, because he can actually assess and quantify sustainability, something that is actually super important in this area. So Goran, please, over to you.
Thank you very much. Please let me know if you can't see my slide.
Yeah,
so I'll talk about sustainability assessments of new materials. I think it's important that sustainability cannot just be assumed. We do need to make scientific assessments of this topic. For example, we know that we must move away from materials based on fossil fuels in order to handle the climate change challenge, but we cannot assume that materials produced from renewable resources are automatically sustainable. That depends on the source of the renewable sources and the production methods as well. So when assessing new materials, I think it's important to have a life cycle perspective to avoid problem shiftings, to avoid that we change problems from one phase of the life cycle of material to another one, and also that we avoid changing one environmental problem to another one. So we need to make life cycle assessments with a comprehensive approach in order to capture both different life cycle phases and different types of environmental problems. So life cycle assessments can be used for assessing new materials and new production methods for materials, and also material choices for products and services. And the idea here is, of course, to make a life cycle assessment to cover the whole life cycle from cradle to grave, from the raw material extraction over material processing and shipping to product manufacturing and packaging, product shipping, product use, product disposal or recycling. And as we know, too often this is not a circular process. Too often this is a linear process, but hopefully the materials can, through recycling, also go back to raw material extraction again. And what we're interested in is, of course, the emissions to air, water, and soil, but also the resources used in terms of material, energy, land, and water. And of course, life cycle assessment has been developed for products, which makes it a bit tricky to work with assessments of materials, of course. We often need to make some sort of assumptions on how the materials are used in different products, etc. But we can also do life cycle assessment specifically on materials and comparing different, for example, different production routes for the same type of material. Life cycle assessment is standardized in an ISO standard, and that's an advantage, of course. It gives a common framework and a terminology, and in this framework, the first phase is the goal and scope definition, where we define research questions, intended application, system boundaries, etc. And for the inventory analysis, the aim is to collect data, make methodological choices, and build a computational model, and then calculate emissions, resource uses, and in the impact assessment, calculate the potential environmental impacts. And then finally, of course, in the interpretation, to explain and understand the results, assess uncertainties, and draw conclusions and make recommendations. And I'll show an example of how results can look like. And this is a complex picture with lots of results, but I'll talk about some of them. This is for environmental impacts and raw material requirements of different power generation technologies. So to the left, there are photovoltaics, then there are concentrating solar power, hydropower, wind power, coal, and natural gas. And these are different environmental impacts, so greenhouse gas emissions, particulate matter, ecotoxicity, eutrophication, land use for these different technologies. We can, for example, see, as expected, that for coal power, we have much higher emissions of greenhouse gases than for the renewable power sources. We can also see that for these is lower. These are coal power with carbon capture and storage. So we can see that we reduce the emissions of greenhouse gases, but they are not eliminated. They are still there, some emissions, and they are typically higher than for the renewable sources. You can also see that there can be differences for different materials. For example, these are for photovoltaics, different material choices in the photovoltaics, and then we see that they produce different results for ecotoxicity impacts of the photovoltaics processes. So that's on the left-hand side. On the right-hand side, there is different uses of raw materials. Obviously, the non-renewable energy demand is highest for the fossil fuels. We can see that the material uses of the renewable sources are typically higher, and they can be very different depending on the technologies used, specific technologies used. So these are examples of the kind of results we can get from life cycle assessment, that we can compare different technologies, we can identify important issues that needs to be further researched and perhaps improved. When we're looking at new materials, there are some challenges, of course. One is, as I mentioned, that we may need to make some scenarios for how materials can be used in the different product systems. And typically, we also often have data for the new materials from laboratory scale or from pilot scale production. And then the issue is, of course, how can we compare this with more mature technologies where we have data for the full-scale production. So here there are different methods for scaling up the production systems and the calculations of the emissions. But of course, it can be a challenge when we only have laboratory data, for example, for new materials. Also, an important challenge is to remember that environmental life cycle assessment, it can produce a lot of interesting information, but it does not give a full sustainability assessment. And I think it's important to realize that different types of sustainability assessment tools can complement each other. I've talked mostly about environmental life cycle assessment, but there is also something called social life cycle assessment, where you try to assess the social impacts across the life cycle for a product or a service system. But there are other tools, for example, environmental impact assessment, which is typically more focused on the local environmental impacts, more site-specific environmental impacts. You may want to do risk assessment of a specific chemical or a specific material or a specific process. And also the raw materials criticality may be important to assess. Raw material use is included in the environmental life cycle assessment, but not really the criticality. It's other aspects that are included there. So I'll end there. Thanks for listening. And I'm happy to take any questions and comments, and you can contact me on this email address. Thank you very much.
Thank you very much, Goran, for this very nice insights into sustainability assessment. And with this, we have come to an end for the talks in this webinar. And now it's time for some questions. And so maybe I can start, but really briefly, with a question for each of you, depending on the talk. So if we could answer very quickly, we don't have much time. So Sylvia, I think this is fascinating that we can create artificial color from nanocellulose, but what are the perspectives on upscaling? I mean, color is everywhere, as you show. How can we actually address this or kind of replace this with sustainable structural color?
I show you, so the point is that to make it truly sustainable, in fact, it's we need to look at different aspects, as Goran was saying. But however, if we really find a way to obtain, like Aji is trying to do, this raw material in a really sustainable way, I think it's the fabrication. It's pretty straightforward because the consumption of water can be really limited. And the recent work, including the one of ours, but also other people, have demonstrated that you can produce them on pretty large scale. So I think the bottleneck now is not too much into the technological aspect, but it's really a chemical engineering problem on the finding a way to, on scale, to extract the material in a sustainable way, which I think it's achievable. And the fabrication, it's mainly additive manufacturing technique. Therefore, you can really satisfy the assessment. And we are also working with people that are doing life cycle analysis of the impact of this material once released in the environment. And so far, we only had positive results in the fact that they are actually not contributing negatively to any of the species that we have studied. So I think it's there is a really bright prospect to this system, but I think the commercial bottleneck comes into having available raw sources with green chemistry.
Okay, which then makes it obvious what the question for you would be, how could we really upscale again and the extraction of these precursors, because under current methods that are not very sustainable, the ligno-boost processes, and it would be nice if you would have one of this universal method that you could target any precursor from biomass. Let's say I want the lignin, I want the cellulose, and I want the hemicellulose, and I want the chitin. How can we? What are the perspectives there at large scale? And I know that you're involved in a spin-out, so tell us more about that.
Yeah, I don't think, so generally, I think there will be different extraction processes, and although there's scope for technology that maybe can take a wide range of feedstocks, I think it's always going to be a group. So let's say it's going to be limited to lignocellulosic feedstock. So crustacean waste, for example, is chemically different. And for example, the process that you mentioned, I don't think it will be helpful to fractionate, the fractionate crustacean waste. It's kind of developed for lignocellulosic biomass, and somebody needs to come up with a very good process of isolating chitin, for example, which is underutilized. We have really a lot of it, also like sort of waste streams available, but we're not really using it properly. I think it's going to be driven, that might actually be driven by demonstrating really nice applications for chitin. And then hopefully that demand will, sort of like inspire people to also work on the extraction method.
Okay. But then for the lignocellulosic biomass, it's kind of possible to get out cellulose, lignin, hemicellulose.
It's possible. So we're doing it already in obviously in paper pulping, and I think additional processes will give us slightly different lignin and slightly different cellulose, for example. So one thing that would be exciting is to get the nanocellulose that Kun Yang and Sylvia need. Maybe we could get it in directly out of biomass. I have a process for that one, rather than first do a kraft pulping and then sort of like hydrolyze those long fibers, chop them down with additional processing. That might be nicer. And so yeah, we definitely, even the old paper pulping processes, there's scope to replace them. They're very chemical intensive, very energy intensive, quite polluting. Yeah, it's worth working on it, but it's really hard to beat these. They've been selected for a reason already, like decades ago.
Okay, thank you. And then Kun Yang, I guess my question is, do you think we would ever fly planes out of biomass?
Yes, since I work in that area, the answer is yes, we will. So planes out of biomass, actually, if you look back in history, back in the 30s and 40s, they are flying planes out of biomass during the war. And now there is actually a big question mark on how do we go back to that, knowing that the last 60 years we gained so much more knowledge behind this, so the composite science and technology area. So the answer is yes, we will. We'll wait for Agie's carbon fiber out of lignin. We'll wait for your battery, Magda and Heather. We'll wait for Sylvia's photonic films to make the windows. And then I'll make the structure out of it, build a wing. And there you go. We have a full lignocellulosic biomass-derived aeroplane, minus the engine.
Okay, that's great. So maybe then following to you, Heather, can we fly planes with batteries made of biomass ever, you reckon?
I mean, I think in the short term, yes, we could fly them very short distances, but it could be that we have complementary technologies. I mean, there's lots of things. It's not just flying the plane, but there are various other operations in the plane that will require batteries. We could have them powering various in-flight things, and it can be complementary to sustainable aviation fuels, say.
Okay, good, yeah. And finally, I guess, Koran, I guess the biggest challenge that I see, and I guess with the life cycle assessment, is where do we actually get the data? And normally the data in the industry is releasing is after they've been releasing the product. And so I don't know, how would you think that things should change in order for sustainability to be actually assessed before something is designed and not after, where a lot of companies tend to stretch it to fill certain environmental goals? How do we make sure that everyone is, saying the truth and we have the real data?
I guess that's a million-dollar question, very important topic though. I mean, we know, for example, from assessments of hazardous chemicals, we know that this is an area where we're lagging behind in the way that society is using much more chemical products than we have good data for. And the way forward here is really, I guess, stronger chemicals regulations that the producers must provide data before actually releasing them on the products on the market. For new materials, this is and for life cycle assessments, there is slightly different types of materials, slightly different types of data that are needed. And that's of course difficult to find, and we are reliant again on the producers here. So more stronger policy are probably needed in this area as well.
Okay, yeah, that's good. So yeah, I mean, we have 5 minutes left until the end, but I think it's also fine to finish a little bit early. So I really hope that we showed you how complex sustainability is. We had only 1 hour. I invite you for more details to read the roadmap, and it's very broad, and even as broad as it is, it still does not comprise everything on sustainability. There's just so many aspects, and particular only if you look at materials, so many types of materials, so many applications, really from how do you make these precursors to more sustainable plastics or biodegradable plastic a solution to, as you see, structural cars, to sustainable materials free of critical metals for our emerging technology, to materials for fashion, materials for various different applications. Someone is now in my door for some reason. Materials for fashion, materials for constructions, and so on. So yeah, very, very complex problem. A lot of work to be done. It's just the beginning, but I think it's something that we really need to seriously start thinking about if we want to progress further. We just cannot continue business as always. So with that, I think we are at an end. Let me know if anyone else has anything to add in the last 4 minutes or so. If that's not the case, I'd like to thank everyone for joining us, and I'd like to thank all the participants online, and yeah, go sustainability of materials and broader. Thank you very much. Bye.
Thank you.
Thank you. See you. Thanks for joining.
Thank you.
Thank you.
Thank you. Bye.